What if I told you that mathematical functions have a secret twin that can run the whole process in reverse? Think of it like a physical machine. If you have a rule that turns x into y, there's an inverse machine that takes that y and undoes the math to give you back the original x. What we're going to do in this video is get some practice identifying when a function can be reversed and walk through a repeatable algorithm to find its formula every time. Informally, an inverse function is simply a rule that undoes what the original function does. But mathematically, we represent this using the notation f inverse of x. But this does not mean f to the power of -1 or equals to the reciprocal of f of x. Instead, the inverse function literally swaps the roles of x and y. F of x to the power of -1 is written as such, whereas the inverse is here as shown. See the difference? All right, let us make sure we're following this properly. Let's say our f of x is defined as a set of order pairs as shown. Then to find the inverse is to swap the value of x and y, as shown when the original function input becomes an output for the inverse function. This implies an inverse of a function means the domain of your original function becomes the range of the inverse, and the range of the original becomes the domain of the inverse, as shown here on the mapping diagram.
Now, we need to understand the fact that not all functions have inverses. For an inverse to exist as a function, the original function must be one-to-one, or injective, meaning that every output comes from exactly one input. A function that has an inverse function is called an invertible function. On the other hand, if a function is not one-to-one, then it is not invertible, meaning that it does not have an inverse function. So what happens when we try to find the inverse of a function that is not one-to-one? The problem is that when we reverse the mapping, what we get is no longer a function, because one input in the inverse relation can be mapped to more than one output. Let's take f of x equals x squared as an example. This is a function, but it is not one-to-one. Here is its graph. If we apply the vertical line test, every vertical line crosses the graph at most once, confirming that it is a function. However, when we apply the horizontal line test, some horizontal lines cross the graph at 2 points. Therefore, the function fails the horizontal line test and is not one-to-one. Now, let's try to find its inverse. Starting with y equals x squared, and we get y equals plus or minus square root of x. This means for any positive value x, y will have two possible values, negative of root of x and positive root of x.
Let's take x equals 4, for instance. For that value of x, y can be either -2 or 2. So the inverse relation would map the single input 4 to two outputs, 2 and -2. This violates the definition of a function, because a function can assign only one output to each input. Therefore, f of x equals x squared with the domain of all real numbers is not invertible. However, we can solve this problem by restricting the domain of the original function to an interval where the function is one-to-one. For example, if we restrict the domain of f of x equals x squared to the non-negative real numbers, then the function becomes one-to-one. Now, when we find the inverse, we no longer need the negative square root branch, so the inverse is equals to square root of x. This works because the original function has been restricted to a domain where each output corresponds to exactly one input. Therefore, an important point to remember is that a function that is not one-to-one cannot have an inverse function unless we restrict its domain so that it becomes one-to-one. So how do we actually find the inverse of a function? First, we have to make sure that the function is one-to-one. If it is not, we can try to make it one-to-one by restricting its domain, as we did with the function earlier. Once we know that the function is invertible, we can find its inverse by following this 4-step algorithm. First, we replace f of x with y to make the algebra easier. Then, we interchange x and y. This is where the swapping happens, because we are reversing the roles of the input and output. After swapping, we solve the resulting equation for y. Finally, we replace y with f inverse of x to finalize the notation and obtain the inverse function. So, in short, the 4 steps are: 1. Replace f of x with y. 2. Interchange x and y. 3. Solve for y. 4. Replace y with f inverse of x. And that gives us the inverse function. Let's try a simple one. Here we have a function f of x equals 2x plus 3. We know any linear function is 1 to 1, so we can proceed with the steps. First, we write y instead of f of x, so we get y equals 2x plus 3. Then we swap x and y and get x equals 2y plus 3. Now we solve for y. We get 2y equals x minus 3 by subtracting 3 from both sides, and then we divide both sides by 2, which gives us y equals x minus 3 over 2. Finally, we rename it f inverse of x equals x minus 3 over 2. This means y equals x minus 3 over 2 is the inverse of the function y equals 2x plus 3. This should be fun. Let's try something a bit harder. Here, our function is a rational one. It says f of x equals 4x minus 2 over 3x plus 1. The first step is to express the function as a form of y instead of f of x, so it becomes y equals to 4x minus 2 over 3x plus 1. Then we swap x and y, resulting x equals to 4y minus 2 over 3y plus 1. Then we solve for y. So first we crisscross and get x times 3y plus 1, which is equals to 4y minus 2. When we distribute, we get 3xy plus x, which equals to 4y minus 2. Then we collect y's to one side and get 3xy minus 4y equals to minus x minus 2. Then we take y as common and get y times 3x minus 4 equals to minus, in common, x plus 2. Now we divide both sides by 3x minus 4 so that y can remain by itself. When we do, we get y equals to x plus 2 over minus 3x plus 4. Therefore, the function f of x equals to 4x minus 2 over 3x plus 1 has an inverse function of f inverse of x equals to x plus 2 over minus 3x plus 4. To confirm you have the right twin, you can test it algebraically, meaning if you compose the two functions, which are the original and its inverse, they should cancel each other out, meaning f of f inverse of x equals x, or f inverse of f of x equals x. This is called the inverse property of a function. Let's see for our latter example. We found the inverse of the function 4x minus 2 over 3x plus 1 to be x plus 1 over minus 3 plus 4. So let's see if it does check out when we verify it with the inverse property. So let's evaluate the composite function of f inverse of x. This means we substitute the function f inverse of x into the x of the original function. Here, f of x is 4x minus 2 over 3x plus 1, so f of f inverse of x will be 4 times f inverse of x minus 2 over 3 times f inverse of x plus 1. This can be solved through multiplication, distribution, and cancellation to simplify the numerator and denominator. We get f of f inverse of x to be 4x plus 8 plus 6x minus 8 over 3x plus 6 minus 3x plus 4. We cancel positive 8 by negative 8 on the numerator and positive 3x by negative 3x in the denominator. Then we get 4x plus 6x over 6 plus 4, which is equal to 10x over 10, where the final result becoming x. Therefore, it is indeed the inverse. If you did not get x at the end, that means somewhere a mistake must be committed, either while evaluating the inverse or while verification, so revise your work to figure it out. Here, we can state the inverse property as f of f inverse of x equals f inverse of f of x equals x. This means composite function is commutative if and only if the two functions are an inverse for one another. You can check the linear function and its inverse by yourself. Sometimes a question may ask you to check whether f of x and g of x are inverses of each other. When this happens, you can check their composite functions. To verify that two functions are inverses of each other, we need to check whether f of g of x equals x and g of f of x equals x, if both composite functions simplify to x, then we can conclude that f of x and g of x are inverse functions of each other. Visually, if you graph them together, the inverse will always be a reflection of the original function across the diagonal identity line y equals x. To illustrate this, we can take the linear function f of x equals 2x plus 3, where its inverse function f inverse equals to x minus 3 over 2. On the graph, we can see the inverse of f of x is a mirror image of f of x. We can see that with the quadratic function as well. Try to determine the intersection point of the two functions, the original and its inverse, for both of them, and let me know down on the comment section. Alright, now let's look at a practical example. Our example says that a private investigator requires a retainer fee of $500 for his services and charges $80 per hour. If he receives a total payment of $1,220, how many hours did he work? Here, we know the total payment, but the problem describes the payment as a function of the hours worked. Therefore, we first need to find the fee function and then determine its inverse function, where the hours worked are expressed in terms of the total fee. First, let's find the function of the fee in terms of the hours worked by interpreting the information given in the question. He charges a $500 retainer fee, meaning that he receives $500 even if he works 0 hours. Therefore, $500 will be our constant term. He also charges $80 per hour. So if he works X hours, the hourly charge will be 80X. Therefore, the total fee can be expressed as f of x equals 80x plus 500, where x represents the number of hours worked and f of x represents the total fee charged. Now that we have our fee function, let's find its inverse, which will give us the number of hours worked as a function of the total fee. To do this, we first write the function as y equals 80x plus 500. Then we interchange x and y and get x equals 80y plus 500. Next, we solve for y. First, we subtract 500 from both sides and get x minus 500 equals 80y. Then divide both sides by 80 and get y equals x minus 500 over 80. Finally, we replace y with f inverse of x and get f inverse of x equals x minus 500 over 80. This inverse function gives us the number of hours worked based on the total fee. In other words, here x represents the amount of fee charged, not number of hours, whereas f inverse represents number of hours worked. Finally, we can evaluate the number of hours by substituting the given fee of $1,220 into our inverse function. When we do, we get f inverse of 1,220 is 1,220 minus 500 over 80, which is equal to 720 over 80, which results 9. Therefore, the PI worked 9 hours to receive the given total payment of $1,220. I will leave you with a couple of questions for you to practice. Give them a try and let me know in the comments section how you did. So, to recap, if we want to find the inverse of a function, we first replace f of x with y, then interchange x and y, solve for the new y, and finally write it as f inverse of x. Also remember that the domain and range switch roles. The domain of the original function becomes the range of the inverse, and the range of the original function becomes the domain of the inverse. Graphically, the function and its inverse are reflections of each other across the line y equals x. Here are a couple of practice questions for you to reinforce your understanding. I encourage you to give them a try and drop your answers in the comments. Then verify your answers by checking the inverse property, just as we did earlier. And that's it. If this walkthrough was helpful, hit that subscribe button and keep mastering math with us here at Rimetric Walkthrough. Thanks for watching, and I'll see you in the next one.